Hi, so this is going to be your lab for your experiment number 19, Vesper theory and orbital hybridization. All right, so this is the pre-lab video. Now you need two things when you work through your lab. You're going to need your online chemistry model, so that's going to be this one here. And then you're also going to want to use this Vesper theory helper. So you can go ahead and open that one up here. Now this normally would have been an activity, but because we're not in there for us to do it together, then I'm just going to give you the key for it. And so what this one is this is similar to the tables that you have in your book. It gives you your electron regions over here, so your number of domains, so that's your number of atoms plus your number of lone pairs. It gives you a generic formula for them. It kind of draws out a picture of what it looks like. And then it gives you the molecular geometries as well as your electron geometries. We also want it because it gives us our hybridizations. Now, whether you have one electron domain or two electron domain, it changes your hybridization. So it doesn't matter whether that's because you had two atoms or one atom, one lone pair, you still end up with the same hybridization. Okay? We're talking about hybridization in our next lecture, so the second lecture of the Vesper theory chapter. But for now, we'll be able to use this chart to kind of guide us through. So we should have our sheet open, right? And so we do have this first page. This is the report page, but this lab is a long one. We have 15 pages in total that we'll be completing. And so it does take, good 4 or 5 hours to complete this. So you want to make sure that you are working on this early because you do need to do all of these other parts. So what we would start with is not this page. You want to start with this section, number 1. So this is our Vesper grouping. And so we're going to go through and we're going to try to follow the direction. So it says draw the Lewis structure of beryllium chloride. And so we want to put in our beryllium, chlorine. Make those a little bit darker. And so now it says construct a model. So when it asks us to construct a model, we're going to go back to our online simulation. So we're going to go to here. Now our simulation should open like this. And so we're going to choose model. We can remove all of those points. And so this is going to be our central atom. So in this case, this is going to be beryllium. So we're going to add in one chlorine and our second chlorine. And what you can do is you can go ahead and click on this bond angles here, and you can kind of see that they fill in what our angle is going to be. So this is the geometry that our chlorines are going to take on in order to maximize the distance away from each other. So when we go back and we look at this, we can kind of see how we have a similar model to something that looks like this. Beryllium, chlorine, and chlorine. And so now we want to go back to our first page and fill in that information. So for beryllium chloride, we should have 2 bond pairs. We have no lone pairs on that beryllium. And so when it's asking for our orbital hybridization, what we're going to do is we're going to go back to our note taker. We're going to look, all right, we have 2 bonded atoms, no lone pairs. So that's going to be our 2 electron regions. It gives us a hybridization of sp. Our Vesper class is this generic formula here. It's us trying to give up a kind of like almost a chemical formula of what the generic part will be. So it's going to be our central atom, and then your number of atoms is X, and since there's 2 of them, then we have it as X2. Our molecular geometry we name, and so for this one it should be linear. And the way for you to check is when you go through your molecular shapes, you can click on your electron geometry, molecular geometry, and you can compare. Now, when we move on to our next part, that was the end of part 2, right? We filled that part in, there's no more questions. We can move on to part 3. Part 3 has us asking about, all right, we need a Lewis structure of boron fluoride. This one's an incomplete octet as well. Okay. We go back to our model because it wants us to build that. So this becomes our boron. We add in our 3 fluorines, and you can see that they've spaced themselves out accordingly, 120 degrees apart between them. So it says go ahead and fill in the report form. So we go back to our report form. We have our boron here. It had 3 bond pairs, no lone pairs. And so if we look at our note taker, 3 atoms, no lone pairs, it gives us a hybridization of sp2. We'll talk about hybridization more in the second lecture of chapter 10, but for now we can use that as a way to fill that in. It wants our generic or our Vesper formula, so that's going to be our AX3 because it's 3 atoms, and then this one's going to be trigonal planar. Now each time we do want to make sure that we are completing that form. This dipole moment we'll also cover in our second lab session, so we can come back to that. We'll look at one more. This is going to be SnCl2. Now the difference with SnCl2 is that Sn has a total of 4 valence electrons. So it takes on a different structure. Instead of being all bonded atoms, we actually have a lone pair here. So when we make our molecule, we can go ahead and remove one of those fluorines. We can add in a lone pair instead. So we get that geometry. We can go back, we can fill that part in. So we have 2 atoms, 1 lone pair. Our orbital hybridization is sp2. We can look here, 2 atoms, 1 lone pair. Orbital hybridization, sp2. And then our Vesper class, this time it's still going to be the A because we have a central atom, but this time it's X2 for our lone pairs, and then X2 for our central atom, or our bonded atoms, and E for our lone pair. Our name for our molecular geometry is also going to change. This one's going to become Ben. Now, there are more than just the Lewis structures and the first sheet that you want to fill in. And so as you go through, you want to make sure that you're following through and you're answering all of these questions. For example, if we look at number 3, when we start to get into our Vesper or our tetrahedral hybridizations, they have you guys build this NH3 here. And then afterwards, they ask us a lot of questions about the repulsions. And so you want to make sure that you're filling in that information, because that's also part of your lab. So make sure that you complete those. The same part as when we go on to our Trigonal Bi-Pyramidals, it has you draw out your different arrangements or your options of where to put those lone pairs. And that has you calculate your repulsions. So you would want to be able to say, oh, there's 4 lone pair repulsions, or whatever that answer would be. So you want to make sure that you go through and you answer those. Now, there is a limitation to this model. One of them is you can see that whether we put in a lone pair or whether we put in a bonded atom, the bond angle is stayed the same. And that's not true. This is treating them all ideally, so it treats them all like they would be the same, but we should know that a lone pair should have more repulsion than a bonded pair. And so this angle here shouldn't be 120, it should be less than 120. It goes to about 2.5 degrees less, depending. Right? And so that's one of the things that we need to pay attention to. Right? That's one of the limitations of the model. As you add in more and more, it goes all the way up to our 8, so the same as our octahedral. The other limitation of this one is that it doesn't allow you to control where your lone pairs are going to be added. So on one of your assignments, they actually have you try to put your lone pairs next to each other. And unfortunately, we're not able to do that. it always adds them into the position that's going to reduce their impacts. And so that's one of the limitations of the model. If you hold on any of the pieces that stick out, you can drag it over in order to rotate your model so you can see it from all 3 dimensions. You can see how we get that T shape now. And so that's one of the benefits of this. So you just want to make sure that you're aware of this, is that they're always going to position your lone pairs where they should be to minimize your impacts. But in your lab, sometimes they will want you to do other things with them. So today, what you want to do is try to go through, identify all of these first 4 columns, and we'll deal with dipoles later on. You want to at least get through your tetrahedral options, filling in your report forms for all of that. So that way you won't have too much to do when you guys get into lab on Thursday. All right. Good luck.